Hello everyone, welcome to my channel. So today I'll solve the problem 2.2 of Pathria. Part A we have already solved. Today I'll solve the problem part B. Sorry for long time I have not uploaded any videos. I'm a little bit busy with my coursework and last week I have tried this problem but I am not satisfied with my result. So though I have made the video but then I have deleted the video. Okay, let's read the problem. The foregoing result seems to contradict the intuitive notion of equal weights for equal solid angles because the factor sin theta is invisible in the expression for d omega. So that if we average out any physical quantity whose dependence on p theta and p phi comes only through the kinetic energy of the particle, then as a result of integration over these variables, we do indeed recover the factor sin theta to appear with the supplement d theta d phi. Very long words. So it takes 2 days for me to realize the problem actually. Okay, let's see the solution and I'll show you what the problem exactly tells and give you a introductive solution. Okay, let's see. So now we are expressing the kinetic term in spherical coordinate system. So check the part A part. There we have solved the Lagrangian, and from the Lagrangian this is the kinetic part. Here these are the quantities. PR is mr dot, p theta is mr square theta dot, and p phi is mr square sin square theta phi dot. So now first understand the problem. Okay, so phase space volume element in Cartesian coordinate, that is d omega equal to dx dy dz dpx dpy dpz. Similarly we can write for spherical coordinate also. So for spherical coordinate d omega is dr d theta d phi dpr dp theta dp phi. Okay, still that everything is fine. Now so here we have converted xyz to r theta phi, px py pz system to pr p theta p phi. So basically we have taken the phase space and converted the coordinates and also the conjugate momenta. Now problem arises from here. In d omega expression there is no sin theta dependence explicitly. This seems contradictory because we expect that equal solid angle in spherical coordinate should have equal weights, which is typically represented the factor sin theta in area element d theta d phi. Now when we are dealing with solid angles in spherical coordinate, the differential solid angle element, this is d omega sin theta d theta d phi. Here the sin theta factor ensures that each differential solid angle element represent an equal area on the surface of a sphere. Now without this factor, areas near the poles like theta equal to 0 or theta equal to pi would be incorrectly weighted compared to near the equator, theta equal to pi by 2. The problem lies in understanding how the sin theta factor reappears when we integrate physical quantities over phase space, particularly when the quantities depends only on kinetic energy term p theta and p phi. I think now the question is clear to everyone. Okay, so let's forward. Okay, consider a physical arbitrary quantity that we have taken ft, function of t. T is the kinetic energy that depends on kinetic energy t of the particle. Now consider the phase space integral of the quantity over the angular momentum p theta and p phi. So this is the corresponding phase space integral. Now actually we cannot solve the equation without taking a function. So let's take a function. So here we are taking the function like e to the power minus at. So here a is a constant and it's like a Maxwell-Boltzmann distribution. You have seen there the exponential dependence. So now we can write f of t is like that. Now theta and phi are independent to each other, so we can divide the integral for theta and phi. So this is for p theta. So this is basically a Gaussian integral. You can get directly from its formula from the Google. I have not written it here, and also for p phi. So if we combining the integral result, so this is the result. So now here you can see the sin theta term. Thus, even though sin theta is not initially visible in the phase space volume element d omega, it naturally arises when performing the integrals over angular momenta, ensuring that the measure in angular coordinates d theta d phi correctly represents equal solid angle. I think now it's clear for everyone. I know this is not the best result, but yeah, from the introduction you can see. If you have any better solution or result, you can comment me. Then maybe I can change my solution later. Yeah, thank you.